But the deal is, we're in chapter 14 now. We've got 4 sections to cover in this chapter, and then that's it for the semester. So basically, we only have 4 sections left in the entire semester. I knew it was probably going to happen that we, kind of got through things a little earlier than usual because, for one, when we test, we don't have to take a whole class day, during class to do it, since it's online. So that takes out a few days and stuff like that. And just we've been going at a pretty good pace, even with days where even with that week, last week, that we didn't have a lot of class. And I end up, you know, having a lot of time, even in a normal in person class in this particular course. So here's my thoughts. So we know that um, after Thanksgiving, we're all online. And honestly, that doesn't really affect us anyway, because we've been online for a while. Um, but what a lot of professors, sorry, have been trying to do is, especially if they are in person right now, and then they know that for the last 2 weeks of class after Thanksgiving, they're going to have to go virtual. A lot of professors are trying to get their semester done before Thanksgiving. And this class would be absolutely perfect for it. Because, like I said, we have only 4 sections to go, and plenty of time to get those done before Thanksgiving. So basically, we could be done learning sections a week from today. And then we would have like a week and a half, or I think it would end up being about 2 weeks before Thanksgiving, where we could do exam 3 and also do the final. I don't want to be rushing anybody, but it is a possibility that we have here in the class. So I want you guys to think about it. I'll probably send an email about it and, just gauge opinions if you guys want to get done early. I mean, it would be one class out of the way, and then you could focus on other classes' finals. But, if it's too much stress to get it done, that's something I want to hear about for sure. So I'll be sending an email so we can figure out. Now, if we don't do that, if we still have the 2 weeks after Thanksgiving, it just means spacing these next 4 sections out a lot, which also isn't a bad thing. Taking it slow is not a bad thing. But yeah, I mean, pros and cons, I guess, really. If you guys do want to decide and get everything done before Thanksgiving break, the sections, I wouldn't have to cover them any faster than usual, so don't think we'd be cramming or anything like that. But anyway, so look for an email, think about it, and we'll figure that out together. But today we will look at 14.1. Let me share my note screen with you. So chapter 14, very different from chapter 13. So chapter 13, those 4 sections that were really, we only did 3 sections in chapter 13 because we skipped that 13.3. That's all we have to do of the integration. So the antiderivatives. We take a little break from derivatives. We go in reverse. We look at the integration. But you guys, in chapter 14, we're back to taking derivatives with a little bit different approach because our functions are in more than one input variable. So this is 14.1. And it's an introduction to functions of several variables. So a lot of times we call these multivariate functions. So here's what we're used to. F of x equals, and then we have, some function of x, maybe it's x squared plus 3x minus 2. So this is a function in one variable. And I know that if you graph this, you would have an X and a Y, you'd have an input and an output. But so it kind of seems like there's two. But when we say a function in one variable, we mean that there's only one input variable. And that's what we've been using basically forever. But you guys, today we're going to look at functions that have more than one input variable. For example, we might have f of xy equals a function. And then on this side, we're going to have both x's and y's. So it might be x squared plus y squared minus 2xy plus 5x minus 7 or something like this. So you notice that the output depends on not only just x now, it depends on both x and y. So it's not really a far jump from the functions in one variable. Function notation still works the same way. It's just that when we do have an input, we're going to have two separate values. So for example, if I wanted to find f of 1, 2 in this particular function, it would mean that I'm putting a 1 in for the x, all the x values, and a 2 in for all the y values. But the evaluation's the same. So this would end up being 1 squared plus 2 squared minus 2 times 1 times 2 plus 5 times 1 minus 7. So we get 1 plus 4 minus 4 plus 5 minus 7. So what do we end up with? 6 minus 7, negative 1. So f of 1, 2 ends up being negative 1. So you might wonder, in like this first version, you put in an x and your output is a y. But in this case, we're putting in an x and a y. So what is your output? You guys, usually we call that z. If we were to graph this, we would have coordinates x, y, and z. So f of 1, 2 equaling negative 1, that would correspond to a point at 1, 2, negative 1, where we have x, y, z. And you might wonder what kind of plane we're in, right? Because our normal,
daylight. Normally, also though, with an election night, the way that it was set up last night, the stage would come right down.
So, you guys, when we do a function in one variable, we put it in x, we get out a y. It makes sense that we graph that in the xy coordinate plane. Because that coordinate plane only has space for x and y. But now that we have x, y, and z, our plane looks a little bit different. It's a three-dimensional plane, you guys, where z is that third dimension. I am apologizing now. I am horrible at drawing three-dimensional stuff. But you're going to see the plane kind of drawn like this today, where this is your x-axis, this is your y-axis. Think about taking the plane from up here and laying it down flat. And then the z-axis is like a height coming up. So we have three axes like this. So to graph a point 1 to negative 1, well, negative 1 would be going down, I guess. Let's see. So you would go to 1 on the x and 2 on the y. So think about a two-dimensional space. It would be kind of right there, but imagine z going down through, straight down. So you'd have to go straight down 1. And I know you can't even tell because I'm bad at drawing these. But yeah, so think about z as being like an up and down situation. Yeah, I told you I'm bad at drawing these. And it never gets better. I've been trying to improve this for like multiple years. Maybe I need to take a class. Anyway, guys, still not a far stretch, you guys. We're adding a dimension. We're adding a variable z that we don't always see. I mean, we don't see z in here, It's just that's what we're calling our output, so we can graph it on an XYZ plane. So you're going to have a lot of just practice working with multivariate functions today. It doesn't really get much more difficult than this right here. You know, you're going to see functions of all kinds. Sorry. You're going to see functions of all kinds. So, for example, maybe I've got f of xy equals the square root of y squared plus 2x squared. And I want to find f of -2, -3. Well, even though we've got a square root function instead of just a, you know, like a normal polynomial, function notation doesn't change, you guys. I'm still going to put in a -2 where there's an x and a -3 where there's a y. All the rules still apply. So I'm going to end up with the square root of -3 squared plus 2 times -2 squared. And I'm going to evaluate. So let's see, I've got the square root here. -3 squared is +9 plus 2 times +4. So I get 9 plus 8 in here. And what's that, 17? So I get the square root of 17. And because that's not a perfect square, I would just leave it like that. So your coordinate pair there would look like -2, -3, and root 17. So nothing too crazy here. You do have a question or two where you have to, well, you don't actually have to draw a graph because we're doing this through an online program, of course. It ends up just being you match a graph to the function. So, and it's not going to be super difficult. I'm going to show you how these graphs look in certain situations. So let's talk about the only graphs we're concerned about. Linear graphs. So you guys, even in a multivariate function, the concept of a function being linear, all that means is any variable in the function is just raised to the first power. So, you know, you think y equals mx plus b in a normal situation. Why is it linear? Because x is just raised to the first power. It's going to be the same here. So our linear graphs are going to have your inputs all just raised to the first power. Oh, where'd I go? I don't know what happened. My note screen just left. Let me get it back and then share it with you again. Okay, you should see it again. I don't know where it went. I probably hit something with my hand. Okay, so the ones you have to graph are not going to be in function notation. So instead of saying f of xy equals something, let's think about it as z equals something. So z being your output. So in a multivariate function, not in function notation, would just basically look the same. Instead of a y equals, we have a z equals. Let's say z equals 3x plus 2y. So notice how this is linear because both your x and y are just to the first power. So you might think, okay, maybe that graphs a line. Well, it is in the three-dimensional space. So instead of graphing a line, what it graphs is a plane. So linear multivariate functions graph planes. And you guys, you'll actually see most of them written with x, y, and z on the same side. So this is how we're used to seeing a function with the output solved for, but you also might see it, let's say we just subtract z on both sides. You might see it as, I guess that would just be 0 equals 3x plus 2y minus z. So notice the output of course, is just to the first power also, but you could note that. Now, here's the question. And I can't use this one because it's a bad example for graphing, but I'm going to give you another example. So in this one, notice I just have a number over here. It happens to be 0 on this one, but it's going to change. And then I have all my variables over here. So again, this isn't in function notation. The output is not by itself, but this is still a linear graph. And it's the way you're going to see it. And a lot of times this is not just a 0. So maybe you'll see 3x plus 2y minus 4z equals 12, for example. Doesn't look like a function, or well, it does look like a function, but it doesn't look like it's in function notation because it's not. Notice your output variable z is not solved for by itself, but because all of these variables are raised to the first power, you know this is going to be a plane. It's going to be a linear plane in that three-dimensional space. So let's just recall back to like algebra 1. If I just had 3x plus 2y, why isn't my pen working very well? What if I just had 3x plus 2y equals 12 and I wanted you to graph that? Well, the easiest way to graph it when it's in a form like this, where x and y are on the same side, is to find x and y intercepts, right? So how would I find the x-intercept? Well, that's where you set y equal to 0, right? So it would be 3x plus 2 times 0 equals 12. The y term goes away, you get 3x equals 12, and you get your x-intercept at x equals 4. And then you would do the same for the y. You'd get the y-intercept. You'd plot those 2 points and draw a line between them. That's exactly what we're going to do here. We just have 3 intercepts instead of 2 because our graph has 3 axes. So let's find the x-intercept. You guys, to find the x-intercept here, we just set y and z equal to 0. So if we do that, we end up with 3x equals 12 and x equals 4. To find the y-intercept, well, to find y, we need to set x and z equal to 0. So you just set the other two equal to 0. When we do that, we'll get 2y equals 12 and y equals 6. And then to find the z-intercept, we'll just set x and y equal to 0. So we'll end up with, be careful with that negative, we'll end up with negative 4z equals 12, and z will equal negative 3. So these are pretty easy to graph. And what's nice is that when you're doing this matching or you're trying to sketch a graph on your own, it'll always say that we're only concerned with the first octant portion. Okay. So you might be wondering what an octant is. In our XY plane, when we're in 2 dimensions, remember we have quadrants. This is quadrant 1, quadrant 2, 3 and 4 because I'm lazy. We just had 4 quadrants. But you guys, when we add that other dimension, the graph is not just broken up into 4 pieces. It's broken up into 8 pieces. All right, I'm sorry, guys. Somebody's at the door. Well, you don't have any clothes on. No. Sorry, guys. Get a knock on the door and it's chaos. So anyway, guys, when you have the X, Y, and Z axis, that three-dimensional plane or that three-dimensional graph becomes a graph that is separated into 8 sections by those 3 axes. So they call it an octant instead of a quadrant. Now, the first quadrant of the plane we're used to has the characteristics that your X coordinate and your Y coordinate are both positive. Well, you can translate that to the first octant, you guys. The first octant of your three-dimensional graph is going to have X, Y, and Z all positive. So when it says that, that's what that means. Now, I don't know why I made that a minus. Did I make it a minus? I did, you guys. So technically, we can't only graph the first octant portion of this because I made my Z a negative. I think maybe we should change it so we can graph the first octant portion. Notice that in the first octant here, if all your coordinates are positive, we would have to be on the positive Z-axis, but our intercept's on the negative, so we wouldn't be able to graph that intercept. And when I made up this question in my head, I wasn't thinking very clearly. So let's make that minor change. So it only applies right here when we first started this graph equation. And then what it would change is when we found the Z-intercept, it would be positive 3. Okay, now we can graph the first octant portion because all of our intercepts are positive. So let me draw that three-dimensional plane situation. We've got your X, Y, and Z axes here. So if we're only graphing the portion where X, Y, and Z are all positive, that means that these axis lines here are going to be barriers for your plane. So for example, the X-intercept here is 4. So take and go 4 on the X-axis and put a point here. Your Y-intercept is 6. So 1, 2, 3, 4, 5, 6. So put a point here. And your Z-intercept is 3. So put a point at 3. Now, because the axis lines, I can't go past them in any way, because if I go past this way, that's going to be a Y that is negative. And if I go past this way, X becomes negative. And I go past this way, Z becomes negative. And the first octant only has positive. So what ends up happening is you're able to just connect your intercepts. And the first octant portion of this graph is just this triangular plane. So it is three-dimensional. So it's like just a flat triangle that's resting its vertices on each of these intercepts. So in your homework, these are the kinds of graphs you look at. They're going to give you something like we had here, and it's going to be in that exact same form where X, Y, and Z are on one side together, then you have some number here. What you're going to do is find the X, Y, and Z intercept and then match that to the graph that has those intercepts on the right axis. And that's it, you guys. That's all we have to graph. You guys, there's tons of three-dimensional graphs out there that are really complicated to draw out and, figure out, and we don't have to really deal with that. All we need to do is make sure we are comfortable with these functions that are in more than one input variable. And really, that's all that 14.1 is doing. You guys just, hey, can you, transition function notation to multivariate functions? Well, yeah, it's not that difficult. Can you graph a simple linear plane? Absolutely. That's really it for 14.1. Your questions look just like examples that we did here. So yeah, I mean, next time we'll start taking derivatives of multivariate functions. That is the goal, not just working with them, but taking their derivatives. But that is for next time. Today is just that intro. So there's that. You'll see that homework up a little bit later on after my next class. And be thinking about, what I was talking about with the schedule and with before Thanksgiving, after Thanksgiving. I'll send an email. I want to really gauge you guys' opinion on it. But other than that, you guys, that's all I have for you today. So I will just see you on, what's today, Wednesday? Yeah, I'll see you on Friday.